All right, so before we begin, I can assure you guys that this presentation will be like the super simplest way of quantum computing, and I'm pretty sure that this will be the most light-hearted presentation you're gonna find on the internet, and we'll try to explain quantum computing majorly through memes. All right, if I don't know if that's possible, but let's find out. So yes, there has been a lot of hype around quantum computing, these days, and there have also been a lot of myths. And I don't know about you guys, but when I started learning quantum computing a little while back, I was afraid to ask what a quantum computer really is, because I was just of the, feeling that this is just a whole another concept, and whatever has quantum in itself, in its name, has to be complicated, right? But you'll see pretty soon that this is not the case here, and we'll help you explore why. So first of all, let's start by why quantum computers. Why are we talking about quantum computers, and just why are we studying it? Why is the world making it? Why is companies putting so many investments into it? But before we study quantum computers, let's just get to know our beautiful classical computers first. So our laptops were not the same, all the while. They were actually first big vacuum tubes that took up a space of an entire room. And since then, research was going on to make the machines powerful, and you know, resulting into the laptop that we have today. So what I'm trying to say is that initially we had these big vacuum tubes where electrons could have moved freely. And what led to such a drastic change in industry was the discovery of transistors, uh, which was also the first industrial revolution of the time. Now, transistors were special because they could act as input to another transistor as well. They could have act as switches or amplifiers, whatever we wanted them to be, and that led to the discovery of integrated circuits, and that enabled us to become, to invent these powerful machines we have today. So the co-founder of Intel, Gordon Moore, actually predicted that the number of transistors on an IC will double every 24 hours. And he said this is a law, that this will happen. This is bound to happen. People will, increase the power of computing by doubling the number of transistors, and this will happen every 24 hours. But later on, he pushed that limit to 12 months, and later on to 2 years, meaning that people were developing so much that the number of transistors on one IC was increasing and increasing and increasing. And this also produced a confusion that we're not sure if Moore's law is driving the chipsets, or is the chipset driving the Moore's law. But whatever it is, hey, we are getting powerful machines every day, every year. And yes, it's very much possible that by the time you are actually cleaning up your code, the the number of transistors per chips are actually, doubling. So every second, every hour, uh, the chipsets is just increasing and increasing, and we are getting more computing power. Manvi, would you like to continue?
Yeah, sure. So moving on, this is the thing that we just had a quite a beautiful review about Moore's law, that yes, the transistors and the chips are increasing, that is increasing the speed, and definitely you wouldn't know before the speed has doubled itself and stuff. But is the Moore's law still active? Is it actually moving on the way it was initially said about to be? And is the flow still the same? I mean, how much can we extend to it? Is there any saturation limit to it or something? So that is what we are exploring here. So definitely Moore's law did have a saturation point, and that is what we have reached Today, we are at a point wherein if we increase the transistors further on, the heat generated will be so much that the silicon technology might even collapse. And that is something to really worry about because, the present situation that we have, for instance, Intel has implemented a 32 nanometer silicon technology. So if we move on further, much further down to it, we might reach a point wherein the transistors are so close to each other that they start producing a lot of heat. Also, if the scale becomes very small, the electrons might tunnel through this micro thin barrier between these wires and it would start corrupting the signals. So definitely we see that despite the famous Moore's law, we have reached a situation where Moore's law cannot be as good as it was initially made to be. The graph is declining, and maybe we do not have that doubling every 2 years theory active anymore. So what do we go on for now? Do we stop developing? Do we just say that okay, we are at a saturation limit or more technological development for now, and that is the speed that we have? Well, not exactly. So we have the second technological revolution, and that brings with us the quantum computers, the brightness and the brilliance of this century, I would say. So what exactly are quantum computers? So quantum computers, or as we have named our entire session to be, these computers or these computational processes make use of quantum phenomena such as superposition and entanglement, which we'll deal in more detail in this session, but I'm pretty sure most of us have idea about superposition and entanglement as in sense of physics. So these computers, they make use of such quantum phenomena to perform computation. And you won't believe the amount of speed that these computers get through these processes. I mean, we have computers that can perform computation
Hello, Manvi. We lost your voice.
Am I audible?
Yes,
Hello.
now it's fine.
Yeah. Did I get unaudible at some point of time or something?
Yeah, last we heard was these computers are incredibly fast.
Yeah, that's what I was saying. These computers are really incredibly fast to just baffle our minds out. So, what exactly the thing is that in quantum computers, the same processor can perform operations on multiple inputs at the same time. Now, this statement itself makes it quite clear why we say that quantum computers are really fast. Because if you have a computer that can perform simultaneously on many types of inputs, it really means that it is doing something worthwhile. So, we move forward and we see how exactly quantum computers came into existence. So first spark of quantum computing was struck by Richard Feynman, and that was like a
Manvi, we lost your voice again.
followed by Peter Shor, and in 1996 we had the Grover's algorithm. These two algorithms really were a turning point for quantum computers, and this was what actually outlined the possibility of these computers. And from here, we've been ever growing in this field, and until in 1997, IBM presented the first commercially usable quantum computer. So we have grown a lot and we are further growing. And as you might see, 1994 is not far from now. So it's a very recent technology we're discussing right now, already in its growing state. I think, Ritvik, you would want to speak from here.
Yes, definitely. So as we have seen that classical computers are reaching a kind of a saturation point, right? So as we all know, Apple just launched its new ARM chip of 6 nanometers. So that's a lot. But what if we do not convert, electrons into digital signals? Like we have all heard of fiber optics, right? So we communicate through light. What we do is we convert light into digital signals. Now, what if I tell you that we don't need to convert it into digital signals? What if we compute on the light itself? So that is the power of quantum computing here, that we actually use ions, or I should say photons, for computing. So as you can see, quantum computers are fundamentally different than classical computers. The most basic building block is different in quantum computer rather than in classical computers. Manu, could you press the next slide, please? Okay, so before we move forward, first of all, it's very important to remove the myth. So many times people think that, in future we may have quantum computers like quantum laptops, and we will be able to browse, and the speed will be lightning fast, etc. But I don't think so that will be the case, at least not for another 30 years, because quantum computers are not here to replace classical computers. We have already beautiful machines for daily web browsing and stuff, watching Netflix and compiling a code. Quantum computers are more or less focused on specific tasks, like developing a vaccine, or simulating a molecule, or simulating nature itself. So quantum computers are very specified devices for a certain tasks, and we always will need classical computers to measure the output of a quantum computer, right? So yes, quantum computers will not replace classical computers, but yes, the processing they would offer will be, greatly larger than any supercomputer we ever have. Like, to compare, if a supercomputer today takes the problem that quantum computers can solve in just a matter of minutes will actually take years on a supercomputer, not hours, but years, decades even. So quantum computers are really that. So we have seen that how quantum computers are different and why we are developing and discussing on quantum computers. But what exactly can, so to give you the best example here, like we were in the midst of a COVID-19 pandemic, and the whole world was searching for the vaccine, and it took us so much time to develop one vaccine, right? It took us around 12 months or more. But if we would have a quantum computer, at our disposal, it would have taken only 1 day to actually compute, and then another 1 or 2 months for building. That's the power of quantum computers, and that's the specialty of quantum computers. And moreover, even in chemistry, like classical computers cannot simulate a molecule, right? The molecule, the nature, they actually work in a quantum manner, and it's very difficult for classical computers to actually simulate nature. As you will see further on, that it's all about combinations, right? So like classical computers at the fundamentals have transistors which consider one possibility at a time, but you'll see further on that how quantum computers can assess thousands of possibilities at the same time. So yes, medicines are one part, and chemistry or nature is another part, and also the cryptography. As I said just now, that it's all about combinations, and cryptography is the most important part, where we use the concept of combinations and permutations to encrypt, and the codes generated by quantum computers will be so tough that it won't break by even the brilliant hacker on earth. So yes, these are the main basic uses. Of course, there are many other, but these are only the basic. And now Manvi will lead us through how quantum computers are already proving themselves.
Yeah, exactly. So we had a lot of uses of what it could do, but now moving on to why we actually came. I mean, somebody came up with an idea of quantum computer and we accepted it would not have been the case. Definitely, quantum computers or quantum computing would have proven themselves to be wonderful at some part. So here we have the case. This is the point where it all started. So one of the most difficult problems of computer science has been to factorize large composite numbers. It has been called difficult because there is no present effective algorithm which can factorize large composite numbers in polynomial time. And what I mean with polynomial time is that the time should be in some linear value. For instance,
Manvi, we lost your voice.
Hello.
We couldn't hear you after the polynomial time.
Yeah, I think there's some network issue on my side. I'm really sorry for that. So, yeah, so the issue with the present scenario is that we do not have an algorithm which can compute the factors of such large composite numbers in polynomial time. And what I mean with polynomial time is that the time complexity of these algorithms which we execute should be in some linear value type of n square, n cube, n plus 7 or something like that. But there's no such algorithm that can factorize composite numbers in a polynomial time. So how do we do that? That is one of the biggest issues. So the solution to this came in form of Shor's algorithm given by Peter Shor, which you might just remember, as I said, marked the starting of quantum computation. So according to Shor's algorithm and in accordance with it, we can actually factorize large composite numbers in polynomial time just if we use quantum computers. So this was where it all started. This was where we got this great relief that yes, quantum computers will be effective. And just to give a breakthrough, quantum computers can actually compute tasks in minutes, which even our supercomputers will take thousands of years to do. So that might give you an idea of how powerful these computers really are. Moving on next. We are here to explore the physics behind it, though the fact is that you might not need much of the physics when you get into computation, but just considering since it's all based on physics, it has always been, so I think you must have a brief idea of what the physics behind these quantum computers and the entire quantum computation thing is. So I know it is not going to be easy because as you can see in the memes present here, these are the most true memes you can see anywhere. Anybody claiming themselves to be physics lovers, I challenge you to explain the entire quantum physics because that is something really difficult to do. It is quite tricky, but yes, we have to get a walkthrough to it. So we'll just give you a quick walkthrough through the basic laws which a quantum computer uses and the basic laws of quantum physics into that. So get yourself freshened up and gear up yourselves for a good walkthrough through physics. So, Prithvik, I think that's your favorite section, so you'd love to explain.
Of course. So basically, we are just going to touch upon just three major parts that are most important in respect to quantum computing. The one is quantum superposition, then the other is quantum entanglement, and the last is interference. So all of this is related to the wave nature of particles. So when we see the world at a macroscopic level, uh, what we see is the classical physics in action. We have certain laws that define things, but when we talk about the microscopic level, like the realm of particles, then we actually come across weird things, right? So, or as Einstein likes to call it, the spooky action at a distance. So these are the three basic most important laws in physics that we are using and implementing it in quantum computing. What I mean by implementing is that we use these certain principles to solve computational problems. So the first, like how these concepts in physics came to action was the famous double slit experiment. So when Thomas Young actually conducted this experiment, he expected it to be a particle behavior, right? Like you just shoot some bullets through some holes in the wall and the bullet will pass through holes and hit the next wall. It's simple. But he didn't see that. He rather saw what you can see here, the result of a double slit experiment. He got bands, and this was later explained by the experiment that electrons are actually in superposition. Like the electron at the fourth band is also present at the eighth. So how is this happening? And then we actually, when we investigated, we found that electrons have a wave-like nature, and this wave-like nature gave birth to the quantum physics as we know today. And what happened in actually the double slit experiment was this, is that the waves interfered, like the waves of electrons interfered with one another. The trough got added into the trough and the crest got added to the crest. And we saw constructive and destructive interference, and accordingly we saw. My one slide back. So understanding the first The first basic, most important of that is uh, the superposition. Superposition is actually the presence of particle at more than one position at a given point of time. So, Manvi, can you show that you know that meme of superposition? Yes. So this is what a superposition looks like. That one particle can exist at two places at the same time. Now, it may seem like magic, but it is not. There have been so much discussion in the physics community about that, that maybe it's not superposition, maybe it's just a state in the universe. But as we witnessed many other phenomenons of quantum physics, we came to know that no, this is not just a state. This is actually much more. So this is actually the truth that one particle can exist at two places with the same and opposite spins. The next important principle is about the quantum entanglement. Quantum entanglement, in simple words, is like if I have a particle on Earth and if I have another particle on Moon or even Mars, and both of these particles are in superposition with one another, so they are actually called entangled, meaning that if I change the particle on Earth, the second particle on Moon on Mars will change itself. And this is what Einstein calls spooky action at a distance. And this is in fact spooky because we are changing one particle at one place and the other particle at the other place will also change no matter the distance between them. These two particles can even be galaxies apart, but they would still show the effect, and that is where physicists came up with different kinds of theories called string theory and the concept of multiverses. But not going into too much depth, the basic idea of entanglement is that if two particles are entangled with each other, they would behave in a similar manner. And there was the third concept, as I told you, about the interference, which actually comes upon the wave-like behavior of electrons. So the two main important parts are here are like the constructive interference and the destructive interference. I'm sure we have all read about it in basic physics that the constructive interference is when amplitudes add up, and destructive interference when amplitude cancel out each other. And electrons do that, or photons do that too. And this could be helpful in our computation. So these three are like the pillars on which quantum computing are actually standing upon. Next slide, please. So yes,
Yeah, and
Einstein
this
just
is
calls
what
it a spooky
Einstein
action.
calls spooky.
Yeah.
Exactly. So that was a lot on physics, of course, and that was a brilliant thing on physics. I think, Ritvik, some of them are getting the vibes of wormholes coming up. So
No, we won't go into wormholes at this point of time. Maybe after the fourth workshop.
yeah, maybe sometime later. But you can actually relate wormholes here after these theories, because some other day, Ritvik and I had a real long talk on them. So they're really relatable with these things. Okay, so moving on next to our topic, that is quantum computing. So we had a lot of physics, and yes, those things do drive quantum computings together. But what exactly is the building block of a quantum computer, and how exactly do you define a quantum computer? Everything was fine. There was physics, there was, not use of transistors and Moore's law and stuff. But there has to be some basis for these quantum computers. So here we come to the building blocks of quantum computers. So we're all aware of bits, the binary system, and the famous zeros and ones that our classical computers use. And that is what make our classical computers worth, the zeros and ones. But similar and much similar to classical computers, we have the quantum computers which use qubits, the quantum bits. And these quantum bits do not exist in one state, like we have the bits of the binary system staying at 0 or at one state, which is the off or on state, or as you might say, the high or low state. But there's no such one state present in qubit. A qubit is actually a superposition of all the possible stable states between 0 and 1 state. So we just read the superposition theory in physics, and here we have the implementation. So quantum computers are made up of qubits, or they understand the qubit language, or in whatever sense you treat bits, it's similar to bits, but a bit different from them in conceptual form. So we come to the basic definition of what exactly are qubits. So as you can see on the screen, just like bits in our computer, qubits make up the whole system in quantum computers. Quite simple to that. But the only difference between them is that a bit can be a 0 or a 1, but a qubit is able to manage all possible combinations among base states 0 and 1. I know that sounds a bit crazy at some point of time, but that is what it actually is, and that is what makes it work so fast. Because, it's all about quantum physics, it's all about the quantum superposition you just heard, so they can exist at all these states. Sometimes we often say that qubits are nothing but actually photons in the wave nature, and because waves have superposition property, they can exist as superposition, so can qubits. So I hope this is something which is quite clear with you, maybe some amount of clear with you. So here we have the theoretical representation of qubits. So you can see this part of my screen. I hope my cursor is visible. So this part, the left side, we have a classical computer or the classical states of bits, which exist in either 0 or either 1. You can see an empty circle and a complete circle, that is, it's either 0 or it's either 1, nothing in between. But when you come to quantum states, or as you can see here, the sphere of quantum, so you see all these blue dots represent one qubit, these yellow dots or golden dots, they represent one qubit. So you see these blue dots, they exist at many places. The reason being that a single qubit can exist in all possible states or all possible stable states between 0 and 1 in this sphere. This sphere is what we call a block sphere, and we'll go in detail about it in the next slide. But for now, so, for instance, we also have this in transistors, that if we have like n transistors, we can have 2 to the power n paths, 2 to the power n possibilities of it. But since a transistor can stay at only one state at a point of time, it cannot exhibit all these states on the same time. But since a qubit can stay in all possible states between 0 and 1 at one point, so if we have n qubits, we will have n states in all possible states between 0 and 1.
We lost your audio, Manvi.
Yeah, till where did I stop? I am really gonna kill this network now. So where did I stop being
To reach the
audible?
power n paths.
Yeah, so that is the point. If we have n qubits, we have to raise to the power n paths available for us, and I'm pretty sure that clears up the things as to why quantum computers are as fast as I just described them to be. Because we have so many paths for just n qubits. So that is the
Can
amazing
I just
part
add
of,
one thing?
yeah, Ritvik.
Yes. So actually, in the theoretical representation, what you're seeing, the qubit is that all the blue dots are actually in entangled state as well. So a qubit
Yeah.
is inside this sphere, and therefore it is in superposition of 0 and 1. That is, it is 0 and 1 at the same time. And all the blue dots which are represented are in the entangled state with each other. That is, affecting any one blue dot will affect all the other blue dots. So that is how a transistor will consider one combination at one time, but a qubit will consider all 2 raised to the power n possibilities at the same time.
Exactly, and that is where we bring all the laws of physics into this one quantum computer. So you see all these dots are entangled. So as Ritvik just explained that in entanglement, if you affect just one of the particles in the entire system gets affected. And that is how if you just do some change to one of the blue dots, all of the blue dots are bound to be affected and to change. So that is how it works with qubits. Moving on next, we have the block sphere and the qubit representation. So what exactly is a block sphere? So you see this sphere here. This is actually representing a plane, and we can consider it like a complex plane. In complex plane, we have these qubits present there. on the sphere, these two dots that you see are actually qubits at 0 and 1 state, and they can exist in the entire sphere at any state which is stable between them. That is what a block sphere represents. It represents, it's kind of a geometrical representation of the qubit system. So here you see when the symbols that are written, like in classical bit we simply write 0 and 1, but here we have written 0 and something not so very a bracket. Well, that is called the ket notation, and that is how we represent qubits. So a ket simply represents a one-dimensional state, or you can say a qubit in a plane. So the plane that we call here, or the space that we call here, is actually called the Hilbert space. So the block sphere represents the Hilbert space, or you can say the Hilbert space is present in inside the block sphere, and this is nothing, simply you can consider it as a space in a complex plane, and these qubits, they exist around and inside the space, and when we represent it in this form, we actually mean to represent a one-dimensional qubit or a one-dimensional structure in the Hilbert space. So this is like a ket notation. It's actually a vector representation of a vector or a qubit vector in form of the classical form that we do. So whenever you see a line and such a narrow kind of a thing, it's a ket here. So that is something interesting about the block sphere and the qubit representation. Ritvik, would you like to add something over here?
You explained it beautifully, but I just wanted to add one more thing, that this is, since in a 3D plane, this is actually a sphere, and the block sphere is actually a boundary that bounds the Hilbert space. That is all the possible states that a qubit might obtain at any point of time. So like a qubit can be present anywhere in this block sphere, and where it is present, that we define by using complex planes, the imaginary and real axis, and for the z-axis we actually use the ket notation, that how much it is 0, how much it is 1. So we actually work on a concept called wave of probability, but that is a huge concept. So just briefly summarizing it, that what we say is, okay, a qubit is 40% 0, 60% 1, and it is present in this complex position. Okay, so this much coordinate of imaginary axis, and this much coordinate of real axis. So like that we define where a qubit is present, and that is nothing but actually the probabilities of how much a qubit is 0 or 1.
Yeah. So moving on next, this is just explaining the block sphere that I just did in a better way. So you see all the block spheres are present inside the ket notations, and they define that they're present into the space and the probability that you can find them. Nothing special with these. Now the challenges, and what are the favorite slides that Ritvik out here?
I love this meme because this summarizes the whole industrial scenario right now of quantum computers. So quantum computers is like a baby to the world. So and there are a lot of challenges we are facing with the quantum computer. So it's all nice and great, but why haven't we achieved it yet? So the first and foremost thing is the scalability. We cannot scale it like as per the early days of classical computers as well. They used to be of huge sizes, filling up the entire rooms. And right now we are at the same stage with the quantum computers as well. So quantum computers at today's age are so huge that they take up an entire room. They take up a full vacuum chamber, not just tubes, but whole chamber. For just one small chip, for just 16 qubits, you need a whole chamber. So it's not scalable, like you cannot distribute it to the masses. The only way we have access to those computers are through the cloud that IBM provides, but that is also limited. The next thing is limited funding. You'll be shocked to know that Microsoft has already spent $300 million on their quantum computer. IBM has spent more than $300 million on their quantum computer. So there is a lot of money being put into this research. This is simply because the material with which we are developing quantum computers are very, expensive. There are chips being built with diamonds, literally, because that has to do with the molecular structure. I won't go into that, but yes, the materials are very much expensive, at least for today. Scientists are working on more better materials to retain qubits. they have imperfect gates. So you'll get to know later on in this presentation that there are actually types of quantum computing, and what we are studying here is model based, like gate based. So like in classical computers, we have AND, NOT, and OR, these three basic gates. Similarly, we have certain gates in quantum computers as well, but they are imperfect. So we do not get a proper result. What we get is a probability that, okay, I'm 80%, 84% sure that they are getting a lot of noise. And the last thing is the decoherence, which is like, I would say, the nature's way of locking out the quantum realm from our realm. Is basically whenever you try to measure a qubit, it collapses into the base as if nothing was ever there. You know, as I'm sure like all of you have heard from all the science fiction movies. So that is actually true. And with quantum computers as well. So whenever we try to retain the data in qubit, we cannot retain the data. Like it is just for some seconds that qubit come into action, and we have to take a snapshot with classic computer. Okay, like this is the like final answer is zero or final answer. So then that, and also that we are not able to make qubits work with each other. Right. So like as bits work with each other, we are not able to make qubits work with each other. So that is one of the most important challenges as well. Manvi, would you please take
Yeah.
forward?
Yeah, so that was a lot of challenges with baby quantum computer. And coming towards what we actually are with today. So we have Google and IBM with the gate model. Like we have 3 to 4 types of quantum computers present here in model present in today's world. So the gate model has been developed to some extent by Google and IBM, and the topological model is being developed by Microsoft, and as you can see, the annealing model is by Google and D-Wave. And also these models have different type of applications, like gate model is basically for calculation purposes and all, and topological model is for, matlab gate model is for research and stuff, and topological model is here for us. So we have a lot of models and a lot of development going on in today's world. Am I right, Ritvik?
Yes, actually, D-Wave has already sold a quantum computer to NASA for $16 billion. And annealing model is basically just for, I should put it like, or for optimization purposes. Like, what's the best possibility out of billions of possibilities?
Yeah. So that is how we're progressing towards making something worthwhile of this quantum computer. And then we, of course, have the simulators, the QTK and QHash, all from Microsoft. So Microsoft's QHash is a dedicated language for programming quantum computers that is under research. We do not have real quantum computers with which we can work today in an effective way, but we have simulators which help us work and code and develop things, and those simulators would give you results as would a quantum computer give if it were present in real time. So the Microsoft's Q Sharp is really a brilliant thing to work on, I'm telling you. And these simulators work really well because they are designed to work accordingly as a quantum computer would. So we really have a lot of codes and algos ready before the quantum computers come into world. So as soon as they come up, they really have a huge stack of codes to run and show out to people. So you can just go on and search these QDK and Q Sharp present on Microsoft, and you can simulate your codes. Though we haven't delved deep into the codes of quantum computers in this session because it was a huge thing to cover, so we're actually keeping it safe for the next sessions to come up. So for now, you can just go and explore them out. We also have Azure Quantum Cloud that provides extra memory space for programming qubits, which require an average PC RAM. So, you have this huge amount of space provided by Azure, that is the Microsoft Cloud Services, and you can just go and explore things out there and have a look at what computers and how quantum computers would work were they present in the real world. So that is an amazing thing to go on with. So are we there with any questions?
Please, you can just unmute yourself and ask away. Okay,
Yeah,
so
we know
one
that.
more thing. One
Yes,
more thing that while we were discussing QDK, that QDK actually allows you to run a certain number of qubits on your local computer. So, like you can code in Q sharp, and you can develop your quantum algorithms for, like to check if your algorithm actually works or not. You may not require a large number of qubits. You would just require a small number of qubits, like just 4 or 6 are enough, and you can just code your algorithm and run it on your local computer. And once you are sure that okay, this is it, I have found my algorithm, then you can actually scale it up. You can scale your software up by many number of qubits and actually run it on a cloud-based simulator, or an actual quantum hardware. So this is where QDK and simulators are, important or useful. And QDK actually runs on .NET, so we are all familiar with it. And Azure Quantum is basically like, if we need n qubits, we actually need to reach the power n bytes of memory in RAM to simulate a quantum computer of that extent. So we might not have that much RAM, locally. So that is where Azure Quantum comes up. Yes, I guess someone was asking something.
Um, yes, sir. My question was that it takes all of the given like possibilities in one instance, and how does it do that? Do that? I'm not able to imagine that. How like
Okay, Manu, would you like to answer?
mm, no, you continue. My network issue will
Uh,
stop in between. I'll peek in.
okay. Okay, so actually, like, let's again go to the hardware aspect. Like in classical computers, we have transistors which acts like switches. Okay, so it considers one possibility at one time. Like, okay, this possibility, then what about this? Then what about this? We developed algorithms to, narrow our search. Like we have binary search and many other algorithms for that. But what happens in quantum computing, since we have superposition and entanglement, we can put qubits in multiple states at the same time, right? And then we can entangle them. So if, say for example, in layman term, if you encountered a block at certain possibility, all the similar possibilities will be blocked for other qubits as well, right? So like this, the most optical thing will actually come up.
thank
That
you.
is that is like how it is. I'm so sorry. I think I lost that photograph. I had one photograph, like you can imagine it like a tree. Okay, so like you can develop possibilities from that tree, like roots and roots and roots. And like say there are in the end we have to reach the power n possibilities long. So rather than using bits of traversing through each possibility at one by one, we actually traverse all of those possibilities at the same time using qubits. Like we need n qubits to be present at these locations, and then we entangle them, and then we just expose them to the problem, and they automatically tunnel through things.
Okay.
Yes, there is actually one more concept of quantum tunneling here, like where qubit from state 1 can directly go into the state 8 through quantum tunneling.
Okay.
Does that clear things out?
A bit. Yes.
I accept. Like even the Nobel Prize winners couldn't, clarify the quantum physics in 25 years, so we are just starting now. But basically, this is how like quantum computing is like done. Like these are the basic principles of how it is, everything is like put together.
Yeah,
I
I
hope.
think quantum physics a lot to take them in because it's a lot to take in at one go. So I am pretty sure there have been a lot of doubts regarding that.
Any other
What?
questions, please? Please, yeah.
That you told about that blue dots, that one, even one dot get entangled, all of the other gets entangled. I didn't get that. What was that?
Okay.
You
Okay.
just let
So
me slide once.
yes, Manvi, go on.
Yeah.
You can explain.
No, no, you explain. You were starting. I was just taking you to the slide. Move on.
Okay. Yeah, I was saying like we discussed the concept of superposition. So these qubits are between 0 and 1. That is, they are in superposition of 0 and 1. They are both 0 and 1 at the same time. Then what we do is we entangle qubits. Like as I told, like the quantum entanglement is a principle. Like if two particles are entangled and they are even thousands of miles apart, changing one particle will affect the other particle as well. Right, so these are called entangled pairs. And what we do here is like we put multiple qubits at different states and we entangle them. Like, okay, if I'll change this qubit, that qubit should also change. So that is how we implement the quantum entanglement principle in terms of qubit. Like
Yeah,
in
it's
real
more like,
computation.
these
Mhm.
particles. Yeah, these particles, they form a system, and the system is like, it can be as large as the entire universe in size, but these particles are actually part of a single system. So I'm just saying about the entanglement in terms of physics. So when these particles, they form the system, so it's obvious that if you change some part of a system, the entire system is bound to be affected in some or the other way. So that is what the entanglement theorem basically states, that if you alter the particles of a system, the other particles present in that system will be affected and will be altered in some or the other way. So here the sphere that you see, here we have particles. So same color particles are actually representing a same system. They belong to a similar system, actually the same system. So when you change one of the particles of the system, all the other particles related to that system change or get altered in a similar manner. So that is what we try to explain with this sphere and the qubits having similar colors.
Oh, so that means it is done manually, so that one, if we change one thing, the other will change automatically.
It's not
Yes.
necessary that it's manual. Change can be in any form, but yes, if you go for an example type of a thing, yes, if we change one of them manually, the others will change. Or even if we change one of them with as a result of some other change or due to some codes or any type of force, any type of reason, so that would change the others. It's just about the
This
change.
is, yeah, this is, as we said, no, this is just a theoretical representation. In real computation problems, like this could, like it's not just necessary that it is in this kind of state. There could be many representations. This is just a theoretical representation that this is the block sphere, like the space bounded by the block sphere. Any qubit can take up a state within this block sphere, and that is called superposition. And then within this state as well, qubits can be entangled. Right, in real computational problems, we can change qubits manually. It's not like turning a doorknob, to be honest. It's more or less like inputting what we, there is a term called weights. So we input weights, we input like how much probable is this outcome to happen, and then accordingly qubits actually tunnel through possibilities and they affect one another. This can be better explained through code, but we are not going into that. So just like this is the basic principle, like this is the basic theoretical representation, like this is how things happen.
Okay, thank you.
I hope it clears things out.
Yeah.
Any other questions? I know it was definitely a lot to take in, and more or less it's very much different than the style we are actually used to. No, actually yes. The question in chat is, so is this whole thing essentially just parallel computing? No, actually, parallel computing is where we execute two tasks, at different cores or at the same time. But, this is actually one task. This is not two separate tasks. This is one task happening at the same time. But there is actually this is a good question. Like there is research going on, like how we can do parallel computing within quantum computing. But the problem is the transportation of qubits. Like in parallel computing, bits are transferred between cores, right? Between chips. But we cannot do it in quantum computing. We cannot transfer qubits. Qubits are very, very sensitive in that matter. So the whole purpose of putting a quantum computer in a vacuum chamber is like there should be absolutely zero interference from the outside world. So like once you assign a task to the quantum computer, then actually you can do nothing with it. The quantum computer just like do things themselves. They qubits actually get into superposition according to the code and everything happens. So like that, it is like different from parallel computing. Yeah. Any other question or any other discussion, like any other feedback or anything else, any other suggestions, please feel free to
Yes,
speak.
guys, please.
This was our first
Okay.
session and we are actually planning much more in the future. Like there is one more popular style of computing, quantum computing, that is coming up is optical quantum computing, in which we actually compute on light. So any kind of feedback will be very much helpful. Did we go too fast? Did we go too slow? Were we clear? How was the memes?
Yeah, I like the session.
Yeah,
Thank
me
you.
too. And the speed was also nice. It was good.
Yeah, your
Thank
memes were too
you.
good.
Okay, we have one more question.
Neither was it too slow and neither was it too fast.
Okay.
There is one question.
Yeah.
Can we go without classical computing, classical computer whenever we get perfect quantum computer?
We can only simulate. That is actually yes. Okay, that is a nice question. So what happens in terms of classical computer is like what is 0 or 1, like in the most hardware aspect. 0 and 1 are nothing like but checking if a capacitor is charged or not. If there is charge present, that means electrons are present, we take it as 1. If the charge is not present, we take it as 0. Right? So this is like the fundamental aspect. But we cannot do that in terms of qubits because qubits will first of all lose their states. They won't stay in state like electrons are. Electrons are much more bounded in that manner. Qubits are much more powerful. They have much more power. They can escape. Second of all, if there are multiple qubits, none of them will work together. Like the problem of decoherence. And one other thing is the quantum tunneling effect. Like as we talked about superposition, like suppose the signal was supposed to be 0, but a photon gets into a superposition state and it is actually 1. So we get corrupted signals. Like a qubit was supposed to travel through the gate, but it didn't. It reflected back and but also gave it an effect like it was passing through the transistor.
Okay.
Yeah, so
Thank you.
all like qubits are made to act in a manner of quantum physics. So like actually in the very most hardware aspect, qubits are nothing but photons and ions. Right, so electrons are charged, but photons and ions are actually the ionic part, right, of a molecule. So we can't manipulate them. They will escape. They have that quantum nature, I would say, yes. They have the quantum nature inherited in them. We are not assigning it to them like bits. So we can't manipulate them. If we'll try to do that, they will just behave in a quantum weird physics, which actually happens. Which that is why quantum physics is different than classical physics. Like at the microscopic level, things get different. So they follow a different set of rules of physics. That is why we actually can't use certain chips. Okay, we have one more question in the chat. Why is it that a quantum computer needs to work at almost absolutely 0 degrees? This is a great question. So actually, what companies are trying to do, they are actually trying to create a vacuum, right? And we are trying to create a vacuum because of the same principle as classical computers. Why were classical computers started with the vacuum tubes? Because vacuum tubes have absolutely zero friction. They have absolutely zero interference. So the best so when we create, and this is essentially important in terms of qubit, because electrons can still pass through copper wires, but qubit can not pass through anything. They actually in vacuum they are actually suspended, right? So uh, if we'll do a further session about the hardware of quantum computer, we'll see like ions are actually trapped through mechanisms called like ion, right? So but if we will compute it at room temperature, there will be a lot of interference from the outside world, first of all being heat. But we want like particles or ions to be totally suspended, like there should be absolutely no interference. So that is why we put it into vacuum. Temperature goes down automatically with vacuum. And then certain they cool it additionally as well to put down the temperature, so that there should be absolutely no energy to be given to ion. Because even if we give a little bit of energy to ions, they'll escape, they will not be trapped as we are trying to do. So that is why we operated at absolutely 0 degrees Celsius and at vacuums. Does that answer your question? Okay, I hope it does. Any more questions? Yeah, thanks. Thank you. Did you enjoy the session? Was the session informative and
Yes, sir.
okay? Okay, thank you. So, Manvi, would you like to add something?
No, I think you've been a lot informative. I was just listening out to you. So we had a brilliant workshop here, and I think there are no more questions because nobody's unmuting themselves anymore. So if you guys do not have any more questions or anything, so we are open for feedback. We'd love to hear from you how you like this workshop. And before ending it, we'd definitely like to have some good feedback or whatever you felt about this workshop.
Also, Manvi, you can stop recording, I think.